Hello students, let's go to next topic of our syllabus. That is nothing but a theorem of parallel axis and perpendicular axis. Before going into detail of this, now question comes in your mind as why we have seen moment of inertia of the body, how to find the moment of inertia of the ring, how to find the moment of inertia of the disc, that also we have seen, and what is meant by moment of inertia, that also we have finished in last minute. Now this theorem of parallel axis and perpendicular axis are there to find out the moment of inertia of a body. Every time it is not feasible to find it out directly by using the formula. Sometimes it is better to calculate the moment of inertia of a body by considering the axis, two axes, one may be parallel or the three axes may be perpendicular to each other, and we can apply that theorems directly and we get the value of moment of inertia. Now this is the reason why these theorems are very important, because these theorems can be applicable to find the moment of inertia of any body. If the two axes are parallel, we can use theorem of parallel axis. If three axes are perpendicular to each other, then we can use the theorem of perpendicular axis. How to use them? To see that, let us consider the first theorem of parallel axis. So let's start with theorem of parallel axis. For this, let us consider this is a rigid body I have drawn here. Any shape of body is said to be, suppose it is any shape of body you can draw. Let us consider this a rigid body. It consists of two axes. One axis is nothing but a MOP, axis MOP, passing from a point O of this body. The first axis is MOP. Second axis is ACB, axis ACB. This second axis must pass from center of mass of the body. So here the point C, we have denoted this C is nothing but a center of mass of this body. So here the two axes are now exactly parallel to each other, and suppose they are separated by distance h apart from each other. Now let us consider any mass dm placed at point D. Let us consider any mass dm here placed at point D. Now here we have to find out moment of inertia at this point D about this axis ACB passing from center of mass, and the axis MOP passing from another point, and the axis of rotation is parallel to axis passing from center of mass. So first of all we will derive some derivation, and finally we will see what is the theorem of parallel axis. Okay, so let's start with here. So in this case, let us suppose moment of inertia of this mass dm about this axis ACB is IC. Same way, moment of inertia of same mass dm kept at point D about this second axis MOP is I0 suppose. Then we can write this as, this IC can be written as equal to integration of, it is a moment of inertia means what? Mass into distance square. So what is the mass here? Dm. Distance square about this is what? Here CD. CD is a distance. So you can write here integration of, so I will write it a bit this side. So here IC you can write equal to integration of CD square into dm. CD square, distance into distance square into mass, or mass into distance square. CD square dm is nothing but a moment of inertia of the mass dm passing from this axis of center of mass about this axis. The moment of inertia is this much. Similarly, moment of inertia about another rod passing from point O is, we have to find out in the same way. So distance from dm is what? Here it is OD. Okay, OD. So equal to integration of OD square into dm. That is nothing but a moment of inertia of same mass about this axis. Remember, this moment of inertias are different because here the distance OD is changed and axis also get changed. That's why definitely they are different. Now here in this triangle ODN, we have to just derive some equation, that is to prove this theorem of parallel axis. First of all, let us elongate this OC and draw the perpendicular from D N such that it will touch to the OC at the point N. Draw this perpendicular. That is modification we have done in this. We have elongated this OC further so that the perpendicular DN reaches at a point N on the line OC. Now just you can write this equation as, I will write it here, I suffix 0 equal to integration of OD square dm. Now here integration of OD square means this. If we consider triangle ODN, it is nothing but a perpendicular triangle. We can use the Pythagoras theorem. Hypotenuse square equal to side square plus side square. So OD square is equal to ON square plus ND square. So same thing we can write here, ON square plus ND square, that is nothing but a OD square into dm. By Pythagoras theorem we have written this ON square plus ND square, that is OD square. Now what is ON square? ON is what? OC plus CN whole square. We can write this as integration of OC plus CN whole square plus ND square into dm. So what we have done, this OC plus Cn is On. Value of On we have kept here. We get this equation. Now use a mathematical formula for a plus b whole square. A square plus twice ab plus b square here. So just use here integration of OC square plus twice OC into Cn into Cn square plus ND square outside the bracket. Here it is bracket, outside the bracket it is dm. So integration of this thing we get. Now OC square is what? See the diagram. OC square is what? It is h. So h square we can write. So this is equal to integration of, in the bracket, h square plus twice h into Cn as it is. Here it should be plus, it should be plus. So Cn as it is plus Cn square. Now let's see. Cn square plus ND square. Let's look at diagram. Cn square plus ND square is what? CD square. So we can write plus CD square into dm. Again we have used here Pythagoras theorem. So we get here Cn square plus ND square is CD square. That we have written. Separate the terms now. So we can write this as, is it okay? Is it okay? Yes, it is fine. Okay. So let's start with this OC plus Cn, On square we have written here first. Let's start with OD square. This OD square, then OD square is On plus ND square, On square plus ND square. On square is OC plus Cn whole square plus ND square as it is. So use the formula a square plus a plus b whole square. A square plus twice AB plus B square plus ND square as it is. Now OC is what? It is a H. So H square plus twice H into Cn plus CD square. Cn plus ND. Cn square plus ND square is CD square. So we reach to this equation. Now in this case what should we do? Just derive the equation. Just separate the terms now. So here it is integration of H square dm plus integration of twice h into Cn dm plus integration of CD square dm. Okay, so we have just separate integration for each term. Now take the constant outside. So we can take this h square outside because h is constant here. So you can write this as h square integration of dm plus twice h integration of Cn into dm plus integration of CD square dm. Okay, so we have written this equation. Now what should you do further? Just put the values and solve the equations. Put the values and solve the equation. So integration of dm. Dm is very small mass that we have considered place at point D. So integration of small mass dm will be total mass of the rigid body, and suppose it is capital M. So you can write here it is h square, here it is capital M plus twice h Cn dm. Cn. So this Cn into dm. Basically mass is kept here and this is another distance. Okay, not related to this. So this according to definition of center of mass, whole mass of the body is supposed to be concentrated at center of mass. So this thing come to be 0. If this thing come to be 0, 0 into anything it will be 0. So we can't write here anything. Now integration of CD square dm. Look at the above diagram. Here in this diagram above this. What is integration of CD square dm here? It is IC. And that CD square dm is nothing but a IC. So you can write plus, it is I suffix C. Left hand side, it is IO. So you can rearrange the term and you can write here moment of inertia about an axis MOP is equal to sum of the moment of inertia passing from the center of mass plus product of mass into distance square. So this is a mathematical formula for theorem of parallel axis. Theorem of parallel axis mathematically can be represented by this equation. So here the moment of inertia about any axis passing from any point of the body is equal to sum of moment of inertia about an axis passing from center of mass, sum of moment of inertia passing from center of mass and product of mass into square of distance between the two axes. So this is IC, moment of inertia of a rod about an axis passing from center of mass, plus m is the mass of the body into h square is a distance square. The distance between two axes is square. So we can say moment of inertia of a body about any axis passing from the body other than the center of mass is equal to sum of moment of inertia of the same body about an axis passing from center of mass and product of mass into square of distance between the two axes of rotation. So this is said to be theorem of parallel axis. So in this fashion we have derived this theorem of parallel axis. Let's go further. Let's go to the next topic of our syllabus, that is theorem of perpendicular axis. Before going into detail, in your book use your brain power they have mentioned. Just try to understand this question, try to find out its answer. Still, if you don't get it, you can ask me, then I will tell you. So this not a blue, it is yellow color question is there. You should concentrate on that question. You should try to find out answer of that question. If you didn't get it, then we will see what should we do. So, but I know that definitely all of you understand that question and you get answer of that one. Now let's go to the next topic of our syllabus, theorem of perpendicular axis. So remember, theorem of parallel axis is applicable when the two axes are exactly parallel. What about theorem of perpendicular axis? As its name contains the word perpendicular. So this theorem is applicable for laminar body, laminar plane bodies in which the axes are three axes you should consider. Let us consider this is a laminar body, any shape of laminar body. Let's consider three axes. And this is x, this is y, and this is z. Three axes are mutually perpendicular to each other, out of which we are going to find out moment of inertia about a perpendicular axis, that is about z axis. Now for this, the remaining two axes x and y must contain the body. The remaining two axes x and y, see, this axis is containing the part of the body, this axis is containing the part of the body, and z axis is now perpendicular like this. Okay, z axis is perpendicular like this. In your book they have drawn like this. Okay, because in your book they can't draw the three-dimensional figure. That's why it is a perpendicular axis. Our aim is to find a moment of inertia about this marker, that means about this z axis perpendicular to plane laminar body, and that is equal to sum of moment of inertia about the two axes which are containing the body, and that is nothing but a theorem of perpendicular axis. Again we will see some parameter here. Let us consider any particle in the body m, any particle in the body at a place p having a mass, suppose some mass it has m has a mass and particle is kept at a point p. Let's draw two perpendicular from point p. One drawn perpendicular on y axis, it will touch to the point n, and this distance pn is x, parallel. Similarly, draw another perpendicular from p on x axis, it will reach the x axis at a point m. So here it is pm, and that distance will be measured as y. So this is y, opposite is y, x, opposite is x, and p is a point. Okay, now here we have to just find out some more derivation again. So let's start with here. Moment of inertia about x axis is equal to what? Moment of inertia about x axis is what? From point p the distance is what? Y. So it is equal to integration of y square into mass is, suppose here we have taken a m, let's consider dm. So y square dm is a moment of inertia about x axis, it is I suffix x. Y axis, it is suppose I suffix y, and z axis I suffix z. So Ix we have find out. Similarly you can write down here Iy, moment of inertia about y-axis. It is a distance of x. So it is what? Integration of x square into dm. That is moment of inertia about y-axis. Now here our aim is to find the moment of inertia about z-axis, and that is nothing but a z-axis. It is sum of these two. So here if you draw like this is x, this is y. Okay, so if you draw it like this, x and so this is y, this is x, this is y. So what should be the value of z? The value of z we can write the square root of y square plus x square, square root of y square plus x square, and that concept we have to use here. So we can write here the moment of inertia about perpendicular axis I suffix z equal to what? So y square integration of y square plus x square into dm. So that is nothing but a y square plus x square gives the z coordinate. So here is nothing but the I suffix z is y square plus x square. So separate the variable integration of y square dm plus integration of x square dm. So we have separated, left hand side remains as it is. Just look at here, y square dm is what? Ix, x square dm is what? Iy. So you can write I suffix z equal to I suffix x plus I suffix y, and this is the equation for perpendicular axis theorem, which says that the moment of inertia about an perpendicular axis perpendicular to plane laminar body is equal to sum of moment of inertia of two perpendicular axes which contain in the laminar body. So this is a theorem of perpendicular axis. So whenever three perpendicular axes are there, out of the three, two contain the body and third one is perpendicular, then you can use this theorem of perpendicular axis. If the two axes are there, one of them is passing from center of mass, other is passing from any point of the object, then we can use the theorem of parallel axis. Now these are the two theorems. You must learn these two theorems. After that they have just taken a two numericals, solve numerical, actually only one numerical they have taken here, example 1.7. From that example they have just applied this one of the theorem. So you just try to understand this and try to correlate how they have used the theorem of perpendicular axis in that example. Similar way we can use the theorem of parallel axis also. So might be all of you see the same application of theorem of parallel axis and perpendicular axis in solve numericals or in exercise numericals also. That are the application base. Now we will see this topic is finished. So we have seen today two theorem of parallel axis and theorem of perpendicular axis. In next video we start with the angular momentum or moment of linear momentum. Okay, so just understand these two theorem and remember this perpendicular axis theorem is applicable to laminar body or plane bodies only. Parallel axis theorem can be applicable to any asymmetric body which has two axes parallel to each other. So I hope you understand this too. We'll stop here. Let's see in the next video, the next part we will see. Thank you.